Hi, in this lesson I am discussing Edexcel IAL January 2022 Unit 6 paper. First question, a student investigated the relationship between length L of column of air and its temperature theta using the apparatus shown. They are showing a capillary tube. One side is open, the upper part is kept open, the bottom part is closed, and there's a concentrated liquid column, that's concentrated sulfuric acid. It's holding some trapped air. A sample of air is trapped inside the tube between the closed end and the drop of the concentrated sulfuric acid. A part suggests why one end of the tube is left open. Okay, so in this capillary tube, one end is kept open. The answer simply I can say to keep the pressure of the trapped air always constant, or to keep the pressure of the trapped air constant at all temperatures. That's the answer. Right. So you might ask, how is it possible to keep the uh, pressure of the trapped air always constant at all temperatures? Okay, I'll little bit explain more, but you don't need to write in the exam paper. Some of you might be interested in that, so that's the reason I am explaining, right? Okay, so if you keep the upper part open, the surrounding is atmosphere, so there will be atmospheric pressure or acting on the top of the liquid column. So there will be atmospheric pressure on top of the liquid column. If I consider the area of cross section of the liquid column capital A, the force acting on top of the liquid column will be PA, that's atmospheric pressure into area. The liquid column has weight, is it? So weight means volume into density into J. Volume of the liquid column is H into A, height of the liquid column. If I say H, area of cross section A, so H into A is the volume of the liquid column into density into G, that is the weight of the liquid column. So a trapped air will exert a pressure. That pressure into area of cross section of the liquid column is the force acting on the liquid column by the air in upward direction. So all these three forces are keeping the liquid column at rest or at equilibrium. So when the liquid column is at rest, all these forces should balance each other. So the total downward force must be equal to total upward force. Divide the whole equation by A, you will get PA, that is the atmospheric pressure that we obtain because upper part is open, plus H rho J equal to P. P is the pressure exerted by the trapped air column. Okay, so now you can see that this pressure of the trapped air is independent of temperature. The left side quantities do not depend on temperature. So the atmospheric pressure does not depend on the temperature of the trapped air. Certainly no. H, the height of the liquid column might change if the temperature increases. So when the height of the or length of the liquid column increases, then density will decrease. So this quantity also will remain constant because we got it from weight of the liquid column. Weight of the liquid column does not depend on the temperature. Is it? Weight is constant. So anyway, so this will be remaining constant at any temperature. Atmospheric pressure remaining constant at in all temperature. So pressure of the trapped air will remain constant even if you change the temperature of the trapped air. So what will happen when you increase the temperature? They are not asking, but it could be a question in Unit 5 paper later. What will happen or why the length of the trapped air increases if they ask? You can say when the temperature of the trapped air is increased, the air particles trapped inside the capillary tube will gain kinetic energy. They will move randomly faster, and the rate of collision with the liquid column will increase, and the rate of change of momentum also will increase during collision. So they will exert larger force on the bottom of the liquid column. So what will happen? This force will become larger, the PA will become larger, these two will remain constant. So this will move up. When it moves up, what will happen? The length of the trapped air column will increase, that is volume of the trapped air column will increase. When the volume increases, the rate of collision, because air particles have to travel longer distance, so rate of collision will decrease. So again, the force will become same as initial force, pressure will become same as initial force, such that to balance the resultant of this and this, again that will be balanced by this one. So that means even when you increase the temperature, the left hand side will remain constant. Therefore, the right hand side, the pressure of the trapped air inside the capillary tube will remain constant. Okay, so anyway, you don't need to write all these things for 1 mark. I just explained there could be students, those are interested about that. Maybe it could be a question in the future Unit 5 paper. So the answer for question 1A part, suggest why one end of the test tube is left, sorry, one end of the tube is left open to keep the pressure of the trapped air constant. That's the answer. Okay, now B part. The student suggested placing the apparatus in a beaker of boiling water and allowing the water to cool. Boiling water is hazard, that's a little bit dangerous in the laboratories when you are using with small children. Right. Explain one other reason why this method may be hazardous. Okay, now you can do the practical anyway. You want to change the length of the trapped air column according to different temperatures. So you can approach that practically in two different ways. One method, as they mentioned, you can keep it in a inside a boiling water and let it cool down. So you at different temperatures you can record the length of the trapped air column. The other one, you can keep the trapped air column inside water which is at room temperature, then boil it. Then heat the water gradually. When the temperature increases, you can record the length for different temperatures. Either way we can do. But here, when you keep this one inside boiling water, the problem is the air will expand a lot. Boiling water means 100 degrees Celsius. The air of the volume of the trapped air might increase a lot. Air inside this can expand a lot, that can push the liquid column out of the capillary tube. So the practical cannot be done after that. If the liquid column has come out of the capillary tube, then there won't be any trapped air column. So you can't do the practical. But that is not true always. If you are using much longer length, that won't happen. But anyway, they are asking that. So the answer could be like this. You can say uh, at 100 degrees Celsius, the trapped air might expand a lot and push the liquid column out of the capillary tube. So it can overflow out of the capillary tube. Then there won't be any trapped air. So practical cannot be continued. That's the answer you should say for question number 1, B part. Question number 1, C part. The capillary tube was attached to a 30 centimeter ruler and placed in a beaker of water at room temperature. The water was heated gradually and theta was measured using the thermometer. Right. State two techniques that should be used to ensure the measurement of theta. Okay, now what they are doing with keeping the capillary tube inside water which is at room temperature. They are heating it, right? So when you are heating it, and you are recording the temperature and the relevant length of the trapped air column. So what are the techniques we should follow to ensure the measurement of theta? Okay, all of you, water should be stirred before taking reading. So better you should say, switch off the heater, stir the water and record the temperature. By keeping the heater on, don't stir the water because the heater is continuously supplied. So you stir the water and when you take the reading, what the temperature might be different. So switch off the heater, stir the water well and record the thermometer reading and the length of the trapped air column. So here about the temperature measurement. So switch off the heater, stir the water well and record the thermometer reading. One precaution. Second precaution, keep the thermometer closer to the capillary tube because you are measuring the temperature of the trapped air, right? But you can't measure the temperature of the trapped air. So you are measuring the temperature outside the trapped air. So you should keep the thermometer closer to the trapped air column outside the capillary tube. So answer 2 marks, 2 answers. Switch off the heater, stir the water well and record the theta. Always keep the thermometer closer to the capillary tube. That's the answer for C part, first part. C part, second part, they are giving 4 readings for temperature 19 degrees Celsius, 35 degrees Celsius, 49 degrees Celsius, and the length of the trapped air column also given, and they are giving a graph length against temperature in Celsius. We normally give that graph during the lessons. If you plot a graph of length of the traptia column against temperature in Celsius, you will get a graph something like this. Temperature in Celsius, and this is the volume or length. You will get a straight line like this. If you extrapolate it, it will cut at minus 273. We know that that's absolute zero. So student also try to do that practical. So, but here the question is, discuss whether the student's measurements would lead to an accurate value of theta absolute zero. The problem is he is taking only 3 readings. They are very closer to each other. So the problem is, you can say like this, it won't give a accurate value for theta at absolute value, absolute zero value it won't give. The reason is, first you can say only 3 readings are taken. So we cannot plot a best fit line by using only 3 readings are taken. Therefore, a best fit line cannot be drawn. Next, you can say those readings are in a smaller range, just from 19 to 49. So that also you can comment. The range should be larger. So you can say 3 marks. The number of readings are only 3. Therefore, best fit line cannot be drawn. The range of the temperature measurements are small. Therefore, the value of theta might have error, might have uncertainty, or you can say the value of theta might not be accurate. Okay, second question. A student investigated lenses law using the apparatus shown. So I add some more apparatus also. The student dropped the magnet into the copper tube and measured the time t for the magnet to reach the bottom of the tube. So how long it takes to fall through the tube, he is measuring. The student had a large number of copper tubes with different lengths x, right? Different length of copper tubes he has. He predicted that the magnet would fall with constant acceleration a inside the copper tube. Devise a plan using a graphical method to test this prediction. So we don't know. We are not interested about whether the prediction is right or wrong. We are not interested in this particular question in this unit 6 exam, in this paper, right? Maybe right or wrong. We don't need to analyze that here. Actually, that is unit 4. It could be a question in future paper, unit 4. They can ask the same question, explain whether the acceleration be constant or not. Or student says the acceleration is constant, comment about it, like 4 or 5 marks they can ask. So I'll discuss that on a separate video, so not here. But practically we are going to check whether the statement, that is student says the acceleration will be constant, whether it is right or wrong. We are going to test it practically, right? So that means if you imagine you have maybe 1.5 meter height or length of test tube, copper tube. If you drop a magnet inside it, the magnet, when it falls through the copper tube of length 1.5 meter, will it move at constant acceleration, or will the acceleration is going to change? That's the purpose of this practical. But we can't measure the acceleration inside the copper tube at different positions. We can't see the magnet. We can't detect the magnet when it is falling or moving through the copper tube. So what are we going to do? Rather than using a much taller copper tube, we are using different lengths of copper tubes, and we are going to measure the acceleration when it falls through. Maybe, for example, 20 centimeter length of copper tube, then 40 centimeter length of copper tube, 60 centimeter length of copper tube, like that. Through different length of copper tubes, when it falls, we are going to measure the acceleration inside that one, right? Okay, so for that, we are going to do a practical. So we are going to explain the procedure of the practical to conclude whether the acceleration is constant or not, right? So we are dealing only with the practical setup and the practical analysis, not the actual statement whether it is valid or not, right? Okay, so for that, first what should we do? Length of the given copper tubes should be measured. We are given different length of copper tubes, so we should measure it by using uh, meter rule. Then we should keep the copper tube in a vertical position. How can we ensure the tube is in vertical position, you can keep a set square aligned with that. So you can ensure whether the tube is vertical. You can attach to a retort stand. You can fit the test tube with the you can fit the copper tube with the retort stand. So the tube will be in vertical position. The copper tube will be in vertical position. Okay, so next you should drop the magnet. When you are dropping the magnet, okay, keep the magnet, the bottom part of the magnet at the upper part of the tube, opening of the tube, and the tube is resting on the or kept on the table. So what will happen when the magnet hits the table, you will hear the sound. Is it like a tick sound? You will hear it. So that means if you keep the bottom of the magnet at the top part of the tube, when the bottom of the magnet hits the table, that means the magnet has fallen through the whole length of the tube. We can take it like this, is it? So you measure the length of the tube. When you hear the hitting sound, you know the magnet has reached the bottom. Some setup, or otherwise you can wait until it comes falling out. If you don't have a table, you have to wait until it is falling down. That also a bit difficult. I feel it's better keep it on a table so you can hear the sound when it hits it, right? Or you can remove the table and you can see when it is coming out. You can switch off the stopwatch. Either way you can approach the practical. So here the idea is you drop the magnet, switch on the stopwatch. When you are dropping it, don't drop it above the tube, because when it is falling from the position to the tube, it will accelerate. We want to keep the initial speed 0 when it moves through the tube. So always keep the magnet just from the opening of the copper tube. So when it comes out of the, when it start to fall out of the tube, you can switch off the stopwatch. So we know that the length of the tube is x. So I'm going to use the equation s equal ut plus half at square. So S means that's the length of the tube, which is x given. Always we are going to keep the initial speed 0. So that's the reason I told always keep the magnet closer to the upper part of the tube. Don't keep it much above. So if this is the tube, keep it like this and leave it fall. Don't keep it like this. So if you keep it like this, when it move from here to here, it will accelerate. So when it reaches the copper tube, the speed will not be 0. So always you should be kept 0. Easy to plot the graph. Plus half into a into t square. T, you are measuring the time taken to fall through it. As I said, you can keep a table. When it hits the table, you can hear the tick sound, so you can switch off, or you can remove the table. When it just come out of the copper tube, you can switch off. A bit difficult, you can try either way. Then what I'm going to do, you are going to plot a graph. So this is the independent variable, because I am changing the length. Because of change in length, the time taken to move through the tube is changing. So x is the independent variable, t is the dependent variable. Normally we draw dependent variable on y-axis. So I can say t square equal 2 over a into x. So this is in the form of y equal mx. So you should plot a graph of t squared against x. That's the idea. If you get straight line, gradient is constant, that is a is constant. Okay, if you are not getting straight line, that means gradient is not constant, acceleration is not constant. That's all the answer. So here you are not going to give a conclusion, you will get a straight line. No, I don't know whether it's going to be a constant acceleration or not. Is not our purpose. You can conclude like this. Plot a graph of t squared against x. If the graph passes through the origin and has a constant gradient or straight line through the origin, that means the gradient is constant, then acceleration is constant. That's all we can say. Okay, so B part, question number 2, B part. Explain a possible source of error in this investigation. So we can say when the magnet falls through the copper tube, it might touch the walls of the copper tube. There could be friction when it slides inside the tube, and if it touches the wall there will be friction. There could be friction that can increase the time. Okay, that could be an error in the measurement of time. Okay, so we are measuring the time only due to the weight and the magnetic force. You know, the same type of question appeared in the unit 4 earlier also. You know, when the magnet falls through the copper tube, there will be rate of change of flux linkage with the copper tube that will induce voltage, and there will be eddy current. Due to current flow, there will be magnetic field. That magnetic field will interact with the magnetic field of the falling magnet. So what will happen? There will be a force on the copper tube as well as on the magnet. But according to Lenz's law, the force will act on the magnet upward direction. So the only two forces we are expecting here is the weight of the magnet and the magnetic force which is acting upward direction. But if the magnet touches the walls of the copper tube, there could be friction. Due to friction, there will be another force. So the time measurement will change. Actually, it will increase. Okay, so that's the possible error. So you can say when the magnet falls through the copper tube, if it touches the walls of the copper tube, there will be friction that will increase the time. That's it. Okay, question number 3. A radioactive source emits beta radiation and gamma radiation. State two precautions. This comes in IGCSE also. Use longer tongues when you are handled with the radioactive sources. Keep the radioactive sources in a lead shielded containers when they are not in use. That's the two answers for 2 marks. Again, I'm telling question number 3, A part. Precautions when you are dealing with radioactive elements. Keep You use long tongs to handle the radioactive source, 1 mark. When the radioactive sources are not in use, keep them in a lead shielded container. Okay, B part. The radiation emitted from the radioactive source can be investigated using the apparatus shown. They are showing a Geiger-Müller tube and a rate meter. The rate meter displays the count rate from all radiation detected by the GM tube. You know, when you keep a radioactive source closer to the GM tube, the GM tube will record the total count if you are connected to a GM counter. If you are connected to the rate meter, it will record the total count rate. The total count rate means the count due to the radiation emitted from the source plus background count rate. I can say the GM counter or the rate meter will record the sum addition, sum of the radiation emitted by the source and the background count, right? Explain why the background count rate should be measured. So why should we measure that? Means first, before starting practical, we should keep all the radiative sources in a lead shielded container and measure the background count rate. Okay. Why should we do that? The reason you can answer, the GM tube or the rate meter will record the total count rate. The rate meter will record the total count rate, which is SUM, sum of the count rate of radioactive source and the background count rate. Therefore, to get the actual count rate of the radiative source from the total count rate or from the measured count rate, background count rate must be subtracted. Background count rate must be subtracted. Okay, so question number 3, C part, the correct count rate. Corrected count rate means after you subtract the background count rate from the measured count rate, you will get the corrected count rate. That's the actual count rate from the radiative source. Is given by C equals C naught e to the power minus lambda t. That is something like activity A equal A naught e to the power minus lambda t. Explain how a graph of L and C against T can be used to determine a value of lambda. So that means part C equal C naught e to the power minus lambda t. LNC equal LNC naught plus, how to take natural logarithm. So ln of this one will be minus lambda t. So ln c equal minus lambda t plus ln c naught. This is in the form of y equal minus mx plus C format. So you can see the graph after plotting the graph. The gradient of the graph or the negative gradient will be equal to negative lambda. So the gradient will be equal to lambda. So you can see the gradient, the magnitude of the gradient or modulus of the gradient, that will be equal to lambda. So you can say we have gradient y equal minus mx, the gradient or the magnitude of the gradient equal lambda. Okay, so that is question number uh, 3, part D. The source contain two radioactive sources X and Y. So the given source contain two radioactive elements, isotopes X and Y. The table below shows the corrected count rate. So they are giving it hours. The time is taken in hours, 0, 2, 4, 6, 8, 10, 12 hours, right? That's the time interval they are using it. And the count rate is given per second. Plot a graph of LNC against time. You know how to take the LN for the given count rate. So you can give it in 3 significant figures, all or 2 decimal points, all the readings. You know how to do that. I can't do it on the board, that calculation. You know, that's normal thing. And plot a graph of uh, LNC against time. You will get a graph something like this shape. Okay, you will get a graph up to 5.38. You will get a graph. You know, LNC against time graph, I already derived it earlier. It could be a straight line. Say C equal C naught e to the power minus lambda t. That is LNC equal minus lambda t plus LNC naught. You know, this is in the form of y equal minus mx plus C format. The graph is like this shape of graph, which is going down. So here there are two different radioactive sources are there, X and Y. They have different half-lives. They are saying isotope X has half-life of approximately 30 minutes. So in 30 minutes, it will become half. So this is actually this time up to this graph. It was up to 2 hours. So in 2 hours, the X will become how many half-lives for X? There will be 4 half-lives, is it? Half, that is first 30 minutes, second 30 minutes, 1 hour, third 30 minutes, 1.5 hours, fourth uh, half-life, that is 2 hours. So during 2 hours, the X will become drop a lot. Is it? The activity will drop a lot during the 4 half-lives. So that's the reason beyond this time, 2 hours, the count rate is much not depending on X. It's mainly depending on Y. Careful. So that's the reason we are getting a graph with two different gradients. So this gradient is there. X is the dominant because it has shorter half-life, means larger activity. You know, T half is equal to ln2 over lambda. Lambda equal ln2 over t half. So t half shorter means lambda will be larger. If lambda is larger, you know activity or count rate A equal lambda, and lambda larger, activity will be larger. So during the first 2 hours, the X is dominating. So the activity is mainly due to X. Y also will be there, but the count rate is mainly due to X because its half-life is shorter, 30 minutes. There will be count rate due to Y also, but mainly this slope, the gradient is giving the decay constant of the X, the isotope X. But after 2 hours, it has dropped a lot, the activity, because that is four half-lives. 2 hours is 4 half-life of X. So its activity would have dropped a lot. Then Y will become dominant. So this gradient is due to decay constant of Y. But there could be X. I am not saying X is completely run out. No, X will be there. But mainly this part is due to activity of Y. The count rate is due to mainly Y because most of the X has decayed already. I hope you understood the reason of the shape of the graph. Okay, so they are saying isotope X has half-life of approximately 30 minutes. Determine a value of lambda for Y. So you need to find the lambda, that is decay constant for y. So better use gradient of this portion. If you try to find the gradient of this one, that will give the x. Okay, so use the gradient of this portion. Even there, we need to draw a big triangle when we are finding the gradient, but better to use little lower part of it. Then most of the x would have gone there. There won't be x because the 30 minutes half life means it would have decayed already. So don't better my advice, don't start to find the gradient somewhere here. But anyway, it's a straight line. Almost you will get a straight line. Find the gradient of this line. So take a clear point somewhere here. Take a clear points, two different points, and find the gradient. So whatever the lambda you are getting, the gradient you are getting here, the gradient is the lambda. That will be the gradient, give the decay constant of y. So if you do it, you will get lambda for that 10.2. I think you will get, yeah, 10.2. So the answer will be, 1 minute, I'll check it. Okay, that is for the third part. Second part, you need to find the lambda. So lambda you will get from the graph of this line, find the gradient. So you'll get 0.068. Yeah, 0.068 per hour. That's the answer for lambda of element y. Right. Next part they're asking to, that is third part, hence determine the half-life of y. So that third part, half-life of y, you found the lambda. So use T half equal ln2 over lambda. So lambda will be ln2 over 0.068 per hour. So lambda will become, that means we are going to find the lambda. We are going to find the half-life now. Half-life will be equal to ln2 over lambda. That will be almost 10.2 hours. You will get it. Okay, that's the answer for third part. D part, third part, question number 3. So understand the meaning of this graph, right? This is mainly due to x. X is the dominant here. Y is the dominant because most of the x has dropped here. Okay. So find the gradient of that. That will give the decay constant of y, right? Okay, question number 4, the last question. A student used the apparatus shown to investigate. So they are letting like a cylinder to hollow cylinder to roll down on a ramp. The student measured the height h1, that is the initial height, and there's a finish line on the ramp. Okay, so the height of the finish line above the bench is h2. Initial height is h1 above the bench. State 2 precautions she should take to ensure the measurement is accurate as possible. So h1, the initial height. So anyway, 2 marks means 2 answers you can say. Even unit 3, these type of questions comes. First, you are going to keep the ruler or meter rule closer to the start line. Keep the meter rule closer to the start line. Ensure the meter rule is at vertical position by using set square. These are the 2 marks you should say. Keep the rule closer to the starting position of the cylinder. Ensure the meter rule is in vertical position by using set square. That's the answer for question number 4, A part, first part. Question number 4, A part, second part. The student measured the initial height. Student measured the height h2. That's the final height. The position where it's ending above the bench is h2. She recorded the difference in height delta h. So the height is falling or rolling down along the ramp, delta h, between the start line and the finish line as 65 plus or minus 1. So she's measuring the initial height h1. You can see the diagram above the bench. She's measuring the finishing line above the bench h2. So the height difference between initial and the final is delta h. So delta h is equal to delta h is equal to h1 minus h2. Both measurements are done by you. They are measured by using meter rule. You know the precision of meter rule is 1 millimeter. Uncertainty in the measurement is 0.5 millimeter. So each measurement, H1 and H2, each of them has uncertainty 0.5 millimeter. So in my theory lesson, I give the link for that lesson in this video also. I already done that. I told that whenever you are adding or subtracting measured quantities, uncertainties will be added. So the question is, explain why the uncertainty in delta H is 1 millimeter. So the answer should be, you can give the answer like this. Uncertainty in the measurement of H1 is 0.5 millimeter. Similarly, uncertainty in H2 also 0.5 millimeter. Since they are subtracted, uncertainties must be added. That's the answer you should give it. Okay, question number 4, part B. So the time measurements for the cylinder to roll down through the same length of slope is recorded 4 times, and 4 different times are given: 2.10, 1.86, 1.94, and 1.89. So B part, first part, question number 4, B part, first part. Calculate the mean value of T and its uncertainty. You know mean value, there are no anomalies. So add the 4 readings and divide by 4, you will get 0.12. So question number 4, B part, first part, mean time. So 2.10 plus 1.86 plus 1.94 plus 1.89 divided by 4, you will get 1.95. Uncertainty, you know, half maximum minus minimum. Maximum is 2.10 minus minimum is 1.86. That will be 0.12 second. Okay, so B part, second part, the student made the RAM less steep by reducing the value of H1. So, you know, initially it was like this. Now he's making less steep. What's the advantage? So explain how this might improve the measurement T. So when you are reducing the slope, right? When you are reducing the slope, or when you are reducing the steep, if it is not steep, what will happen? The compound of the force along the ramp downward will decrease, so acceleration will decrease along the ramp downward. The acceleration will decrease, so the speed will decrease. So what will happen? The time taken will become larger. The time taken to move from the initial position to final position will become larger. So when the time measurement becomes larger, what's the advantage? Percentage, you know that. Yeah, that also I mentioned in my theory video. When you increase a larger measurement, the percentage uncertainty will become smaller. Percentage uncertainty will become smaller. That's the advantage in this method. Okay, question number 4, part C. The student, two students each carried out this procedure for another value of delta H. They recorded the following times for the same value of delta H. So they are doing it separate value of delta H, not, so that's the meaning of another value of delta H means the delta H not same as earlier as 65 plus or minus 1 millimeter, some other value, but they are doing it, both students are doing for the same delta H, but not 65 millimeter as they mentioned in A part, second part, some other value, but they are getting the same, they are doing the same delta H, right? They recorded the following times for the same value of delta H. So they are giving the time measurements, repeated time measurements for A and B. A is getting 2.45, 2.50, 2.38, 2.45. The mean time of A is 2.44, the repeated measurements. For B also, different values are given, the repeated measurements, but the student B also getting the same average value, 2.44. Compare the accuracy and precision of the data that each student collected. Careful the word about accuracy and precision. Where do we use accuracy? Where do we use the word accurate? Where do we use precision? So we can use the word accurate if the value you obtained is more closer to the actual value. We can say it is more accurate. So the word accurate is used if the measurement made by us is closer or equal to actual value. We say our measurement is accurate. But what do you mean by precise measurement? Precise measurement means you are taking repeated measurements. If the repeated measurements are closer to each other, if the repeated measurements are closer to each other, then we say the measurements are precise. So closer to each other does not mean accurate. So for example, you are doing some practical to find the gravitational acceleration, and you are getting values of g is equal to maybe 4.81, 4.80, 4.9, 4.80, maybe 4.79 and 4.82. Right, these are the values you are getting for g. So these values are precise. They are very closer to each other. But are they accurate? No, we know that G is 9.8, so they are not accurate. Maybe systematic error is there, right? But here we can say these values they are precise measurements. That means they are very closer to each other, but not accurate. So the meaning of precise and accurate, accurate means the measurements are closer to the actual value. Then we say it is accurate. If the measurements are closer among them, the repeated measurements are closer to each other among them, then we say precise. But precise does not mean it is accurate. Okay, so in this question, they are saying compare the accuracy and precision of the data that each student collected. Both are getting different values of repeated measurements, but average, the mean value is same for both, 2.44 seconds. So we can say both A and B got the same mean time. Both have the same level of accuracy, but we don't know the actual value. But the level of accuracy is the same. We don't know the actual value, whether it is 2.44 or 2.68 or whatever it is, but they have the same level of accuracy. If I say A is accurate, then B also will be accurate. If the accurate value is somewhere 2.45 or something like that. But if the actual value is 2.95 or 3 seconds, then we can say both are wrong. Both are wrong because both are deviating much from the accurate value. So here we can say since both A and B are getting the same mean value, they have the same level of accuracy. That means if A is accurate, B will be accurate. If A is not accurate, B will not accurate. But we don't know the actual value, right? Then we can find the who is more who is taking more precise value. So find the difference between the largest value and smallest value for A and B separately. So to find the largest value of A, you can say 2.50, that is the largest time measurement by A, and the smallest time measurement by A is 2.38. So the difference is 0.12. For B, the difference is 2.48 minus 2.40, 0.08. So A has big difference among the readings. So that means the readings taken by A is not precise, but the reading taken by B is more precise than A. Okay, that's the answer you should give here. Okay, question number 4, part D. The relationship between time t and the acceleration of free fall g is given by this value. They are giving it. Where s is the distance along the ramp between start and final. So that's along the ramp. The distance is all the values are given. Time measurement is given with uncertainty. S is given with uncertainty. Delta h, that is the height between the initial and the final positions. Given. Determine a value for g. Symbol, just substitute first part. So make the g subject. G is equal to 4s squared over t squared times delta h. Substitute, all the values are given. 4 into s is given as 80 centimeters. Convert to meter. So 80 into 10 to the power minus 2 all things squared over t squared is given in seconds. So 2.44 squared into delta h is given in millimeter, convert to meter, so divide by 1000, 43 into 10 to the power minus 3, all things squared, solve it. You will get the answer, give it in 3SF, 10.0 meter per second squared. Okay, so determine the percentage uncertainty in the value of G. Okay, so second part I'll do it here. Second part, percentage uncertainty. So I can say percentage uncertainty in G. You can see that numbers have no percentage uncertainty, only the measurements or the quantities obtained from the measurement, they will have uncertainty. So this is actually s squared is divided by t squared into delta h. So I told that whenever quantities are divided or multiplied, they must be, the percentage uncertainty should be added. So I can write percentage uncertainty in G equal percentage uncertainty in s squared plus, that's the top part, plus percentage uncertainty in t squared delta h. Right, one by one we'll solve it. Percentage uncertainty in s squared. So go through my video regarding the error calculation lesson. I'll give the link for that. X to the power n means n into x to the n into percentage uncertainty in x. So the index comes from. So percentage uncertainty in s squared means 2 times percentage uncertainty in s plus percentage uncertainty t squared into delta h. When two quantities are multiplied, we need to add the percentage uncertainty of them. So plus, I can say, if I solve this part, I can say percentage uncertainty in t squared plus percentage uncertainty in delta h. I hope you understood it. So whenever two quantities are multiplied, and if you are, say, for example, z equal x into y, percentage uncertainty in z is equal to percentage uncertainty in x, percentage uncertainty in x plus percentage uncertainty in y. They must be added. So here t squared and delta h are multiplied. So percentage uncertainty of t squared delta h means percentage uncertainty in t squared plus percentage uncertainty in delta h. Okay. So exam, you don't need to write all these tests, but for your understanding, I'm writing. So here again, I can write this one same, 2 times percentage uncertainty in S plus percentage uncertainty in T squared. Same thing like, Z equal X to the power N means N times percentage uncertainty. So percentage uncertainty in Z is equal to N times percentage uncertainty of X. So if there's an index, the index comes front. So that will be 2 times percentage uncertainty in T plus percentage uncertainty in delta H. Okay, so now only thing we need to substitute. So in the exam, those who are good in doing this quickly, you don't need to write this one. You can, from here, you can directly jump to this one. Anyway, for your understanding, I wrote step by step. So this is going to be 2 times percentage uncertainty in S equal uncertainty in S divided by value of S. Uncertainty in S is given plus or minus 0.1. So 0.1 over 80 centimeter. Both are in centimeters. So I don't need to convert to meter because the conversion will cancel up and down or numerator and denominator. So I am not cancelling, I am not converting it. So 100% plus percentage uncertainty 2 times percentage uncertainty means that is time uncertainty is 0.04. So 0.04 over time measurement is 2.44 into 100% plus percentage uncertainty in delta H. So delta H also given in millimeter, uncertainty also given in millimeter, 1 millimeter. So keep both in millimeter, 1 over 43 into 100. Okay, solve it. We normally give it in 2SF. You will get 5.9%. Okay, if you have any difficulties or confusions in writing these things, finding the percentage answer, if you have any confusion, you can do the following method. There, I will find the maximum value of G by using the uncertainties given. I will find the minimum value of G by using the same uncertainties given. I can find the half G max minus G min, maximum half into maximum G minus minimum G over actual value of G already, divided by the value of G we obtained. That is, we found it already 10.0 in D part D, first part, right? So that method also I'll do it as a second method for this question. Okay, so the same thing, 5.9, I'm going to get here also, method 2, right? Second method. Uh, right, so this is the equation for G. I'm going to find the G max, maximum value of G. To get the maximum value of G, the advantage of this method, I don't need to find the percentage answer. Finding the percentage answer, too much of mathematics coming. Sometimes some students might get confused. So you can follow this method. So to get the maximum value of G, I should use the maximum value of S. How can I get the maximum value of S? There is uncertainty for S. So if you add the uncertainty with the value of S, you will get the maximum value of S. Say for example, S is given as 80 centimeters plus or minus 0.1 centimeter. So S max means 80 plus 0.1. So 80.1 centimeter is the S max. S minimum means, later I need that, S minimum means minimum value of S is 80 minus 0.1. Minus 0.1. So that is the minimum value. Like that, for each and every quantities, I'm going to find the maximum and minimum values. Right, so I'll do that method. So G max equal 4S squared, S max squared, maximum value of S. So you know that IGCSE mathematics on a fraction, if you want to get a maximum value, the denominator should be the minimum. So T minimum I should get. Delta H also I need minimum. Okay, so 4 times S max, I already told that is 80 plus 0.1, that is 80.1. So 80.1 centimeter convert to meter, all things squared, divided by time is given as 2.44 plus or minus 0.04. So minimum time is 2.44 minus 0.04. That will be 2.40. That is 2.44 minus 0.04 is 2.4. So I'm going to take that place. So 2.40 squared into delta H. So delta H is given as 43 millimeter plus or minus 1. So minimum delta H 43 minus 1, that is 42, convert to meter. 42 into 10 to the power minus 3. Solve it. You will get the G max That will be 10.6061. Yeah. Right. So I need to find the G minimum now. So I need to find the G minimum means. Okay, so G minimum means the numerator should be minimum 4s minimum squared over T maximum in a fraction. The denominator should be maximum into delta H maximum. Okay, so G minimum will be uh, 4 S minimum you will get 80 minus 0.1, so that will be 79.9. So 4 into 79.9 convert to meter, so 10 to the power minus 2 all in squared divided by T maximum, that will be 2.44 plus 0.04, 2.48 into delta H maximum, that also you should add 43 plus 1, 44, convert to meter, solve it, you will get G minimum, that will be 9.44. So I need to find the percentage uncertainty. G max half into minus G minimum over value of G what we obtained, that is 10 into 100%. So that will be half. G max is 10.61 minus 9.44 over 10.0 into 100. You will get the same answer, 5.9%. So here I did not find the percentage uncertainty. Without finding the percentage uncertainty, I found the, sorry, I didn't find the equation for percentage uncertainty. I found the percentage uncertainty directly by using the G max and G minimum. Okay, so next part, that is the last part, deduce whether the value of G is accurate. Okay, simple. Those who have followed this method, you can answer simply the third part. Those who have followed this method in the part D, second part, if you would have done this method, part 3, the third part, you can give simply the answer, just that's also 2 marks. So deduce whether the value of G is accurate. You know the value of G, actual value is 9.81. So you can see the G minimum is 9.44. So experimental value of G in the range of 9.44 meter per second square to 10.61 meter per second square. Actual value is 9.81. That is falling within this range. You can find that. That is falling within this range. So those who have done the second part, D part, this method, you can use your answer. In the third part, you can see the experimental value of G is within the range of 9.44 meter per second square to 10.61 meter per second square. Actual value is 9.81 meter per second square, is falling within this range. Therefore, my experiment is acceptable and accurate. Simply you can finish the answer, right? Okay, those who have done my first method, finding the percentage uncertainty by using the equation method, that is, I wrote as a first method 2 times percentage uncertainty in S plus 2 times percentage uncertainty in T. That method those who have followed. To answer the third part, you need to find the uncertainty here. So those who have done the first method for question number 4, D part, second part, those who have found the percentage uncertainty by using the equation method of percentage uncertainty, that is 2 times percentage uncertainty in S, 2 times percentage uncertainty in T, plus percentage uncertainty in delta H, those who followed and found 5.9. Now you need to find the uncertainty for the third part. So you can find the uncertainty in G equal, you know the value of G 10.0 into you found the percentage uncertainty 5.9 over 100. So you will get the uncertainty will be plus or minus 0.59 meter per second. So now find the range. You are finding the range now only. Those who have used G max, G min in the second part, they already found the maximum minimum, but you are finding the maximum and minimum value of G now only. So range of G you are going to find. Therefore, G is equal to 10.0 meter per second square plus or minus 0.59 meter per second square. So the experimental value range will be 9.41 to 10.59. Okay, now you can give the conclusion. Actual value of G is 9.81 meter per second square. That is falling within the range of my experimental value. The actual value 9.81 is falling within the range of my experimental value. Therefore, the experimental value is acceptable. You can give the final answer like that. Okay, so this is for the students, those who found the percentage uncertainty by using the first method where you use the equation 2 times percentage uncertainty of S plus 2 times percentage uncertainty of T plus percentage of delta. That method, those who followed will follow this method. Okay, so there is one more method to answer the third part. You can find the percentage difference. So, or you can do method 3 actually, this one, because I already explained two methods for the third part. Method 3, find the percentage difference in G. Your value is 10, actual value 9.81. So difference 10.0 minus 9.81 over 9.81 into 100%. So that will be 1.9 percentage. You can see percentage difference 1.9, percentage uncertainty we found it earlier 5.9. So you can see percentage difference which is 1.9 less than percentage uncertainty which is 5.9. So I told that any experiment to be accepted, percentage difference must be smaller than percentage uncertainty. So I can say since percentage difference less than percentage uncertainty, you can say experimental value of G is acceptable. Is acceptable. Okay, either way, you can answer this third part. I hope you understood this January 2022 paper. Okay, right.